Chapter 4, Reactions in Aqueous Solutions. Okay, so a solution is a homogeneous mixture of two or more substances. It is not the answer to a problem. Solutions can be in the liquid state, in the solid state, or in the gas state. A solution contains two different substances, or it can have more than two substances, but a minimum of two. One is the solvent and one is the solute. The solvent is the one that's present in largest amount. We are going to be talking about aqueous solutions. Aqueous means dissolved in water, so the solvent in aqueous solutions is always water. The substance that's present in lesser amount is called the solute. That's the substance that's dissolved in the solvent. Here are some examples of solutions. Many of the substances that we encounter in our everyday lives are actually solutions. They're not pure compounds, they're not pure elements. There is air in the room. That's a good thing, or we'd all be dead, right? Air is a solution of gases dissolved in other gases. It's a homogeneous mixture. It's not a pure compound. And so in air, we have nitrogen, oxygen, and argon gases as the primary gases, and there's some other ones as well. Oops. The primary gas is nitrogen, and so that would be considered the solvent, and the other gases would be the solutes. We can also have liquids dissolved in gases. There's also water vapor in the air. Humidity is gaseous air. It's liquid water dissolved in the gaseous air. We can have gases dissolved in liquids. Anything that's carbonated, a carbonated beverage, is carbon dioxide, which is a gas dissolved in water. Liquid and liquid. Vinegar is acetic acid in water. Acetic acid is a liquid in its pure form. So you have two liquids dissolved, mixed together. Salt water. You have a solid dissolved in a liquid. And we can also have solid solutions where you have a liquid dissolved in a solid or solids dissolved in other solids. An alloy is a homogeneous mixture of different metals. It's actually a solution, a solid solution of different metals. So sterling silver is copper dissolved in silver. Dental fillings, mercury is a liquid, mercury dissolved in silver. And you can actually also have gases dissolved in solids. Those are just examples of solutions. So we talk about electrolytes and non-electrolytes. And you've probably heard of electrolytes, and you know that when you play baseball or any sports out in the really hot weather and you sweat a lot, you need to replenish your electrolytes, right? They advertise this on TV, and they're trying to sell you Gatorade or Powerade. Electrolytes are substances that, when dissolved in water, give a solution that will conduct electricity. Electrolytes in your body fluids are very important because there are a lot of electrical impulses that cause your body to function. And without the proper electrolytes in the different solutions in your body can't function correctly. So an electrolyte gives a solution that conducts electricity. A non-electrolyte doesn't. It's not an electrolyte. It will dissolve in water, but that solution does not conduct electricity. So here are two examples, and these are both present in Gatorade. Sugar. When sugar dissolves in water, here's solid sugar, and here we have the reaction arrow with H2O above it, meaning we're dissolving this in water, and then we get aqueous sugar molecules. The sugar molecules separate and form a homogeneous mixture with the water, but the molecules themselves are still the same. There's nothing charged here. Electrical current is the flow of electrons. And in order for a solution to conduct electricity, there has to be something that can carry the electrons. Sugar water doesn't conduct electricity. When you dissolve something like salt, sodium chloride, in water, the sodium ions and the chloride ions separate from each other. And now the sodium ions and the chloride ions are available to carry the electrical charge. The presence of the electron, of the ions, is what enables it to conduct electricity. I thought I had a picture. Oh, the picture's coming later. Never mind. So here are two words that are similar, and yet the difference is important. Dissociation versus ionization. Dissociation refers to an ionic compound breaking apart into its ions. So when sodium chloride dissolves in water, it separates into its individual ions, but those ions were present in the solid sodium chloride. Dissociation just means they dissociate, they stop associating with each other, they separate. Ionization refers to the process in which a molecular compound forms ions when it dissolves. And so what this applies to are acids. We talked about acids being molecular compounds that dissolve in water to produce hydrogen ions. HCl is not an ionic compound. It's a covalent bond between hydrogen and chlorine, and there are no ions in pure HCl, hydrogen chloride. But when you dissolve it in water, it forms ions. It becomes ions. It is ionized. Okay, so dissociation, just separating pre-existing ions. Ionization is forming ions where there were not ions before. So, would HCl dissolved in water conduct electricity? Yeah, there are ions. If it forms ions in solution, then it's considered an electrolyte. Any questions yet? Mm-hmm.
Is it like if the products have a charge, then they're electrolytes?
Yeah. So if the products have a charge, if the products have ions, then it will conduct electricity and it will be an electrolyte. There are strong electrolytes and weak electrolytes. Strong electrolytes separate completely into ions, and weak electrolytes only ionize a little bit, but they're mostly intact molecules. So in the strong electrolytes, we have ionic compounds that are soluble in water. An ionic compound that is soluble in water will always separate completely into its ions when it dissolves. And then there are 7 acids that are considered strong electrolytes. They're called strong acids. The strong acids are strong electrolytes, and they are listed over here. We should memorize that list. So, hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric, chloric, perchloric, and sulfuric acid. When these substances are dissolved in water, they separate completely into ions. They form ions. They're ionized. Weak electrolytes only ionize partially. Weak electrolytes are going to be molecular compounds that ionize a little bit. So acids form ions in solution. They form hydrogen ions, but not all of them are ionized completely. So these are called weak acids. Any acid other than those 7 is a weak acid. They ionize a little bit, but not completely. They're actually present mostly as intact molecules. They're still considered an acid, though, because they do produce some hydrogen ions in solution. So here we have an illustration showing the difference between non-electrolyte, weak electrolyte, and strong electrolyte. So this is a conductivity apparatus. It's a light bulb attached to a power source, but the power comes in and goes from one electrode and has to go through the solution to the other electrode in order to complete the circuit and turn the light bulb on. This one is in pure water. In pure water, there aren't any ions. And so we've got these individual water molecules there are no ions, there's nothing to carry the electrical charge. Pure water does not conduct electricity. So why do we have to be careful with electricity around water? Well, there's a couple of different reasons. One thing is, most of the water that we encounter is not pure water. You know, if you've been watering the backyard and there's water all over the deck, and then you're plugging in power equipment, is the water on the deck pure water? No, it's probably got some stuff dissolved in it. Even tap water will conduct electricity a little bit because of dissolved minerals. The other thing is, if you have a high enough voltage, like from a lightning strike, or even 12 volts or 9 volts can even do it, you can actually electrolyze the water and form ions that way, and so that will cause a problem too. But pure water does not conduct electricity. So here we have a weak electrolyte. In a weak electrolyte, we do have intact molecules. Most of this would be a weak acid. Most of these are intact molecules. Only a few of them have separated into ions. So there are a few ions available to carry the electrical charge. The negative ions are going to flow towards the positive electrode, and the positive ions are going to flow towards the negative electrode. And so we'll see this light bulb, it just kind of glows because it conducts electricity a little bit. In a strong electrolyte, all of the molecules ionize, or all of the ions dissociate, and so we have more ions present. More ions present can carry more electrical current, and the light bulb will glow brightly. So strong electrolyte, strong light bulb. Weak electrolyte, weak glowing light bulb. Non-electrolyte, non-glowing light bulb. Any questions? How do you, yeah?
I have one question.
Uh-huh.
The strong electrolyte, so would that mean that the positive charge is what's carrying the, because I know in this case they're both disassociated, so we have both negative and positive, we have equal amount, but would it be the positive?
The negative ions flow towards the positive electrode, and the positive go towards the negative. So essentially the negative ions go to the electrode and actually give up the extra electrons, and those electrons can flow through the wire, and then when it comes around the other way, at the negative electrode, these ions become neutral atoms again by picking up the electrons. So there's actually a chemical reaction that's involved. Yeah, it's a little more than that, but yeah.
If they become neutral when they get when they get closer to the electrodes, does that mean the longer you just have that solution sitting there, it'll eventually run out?
Yeah, if you had a solution here and you left this running for a long time, you would probably deplete all the ions in the solution, because chemical reactions generally will occur at the electrodes. And like many of the things I'm teaching you, we're teaching you like the top layer, right? And you peel that back and there's like this big cavern underneath. And sometimes I'll say, we don't really want to go there, because the explanation would take like 2 months. So, yeah. Any other questions? It's good to have questions. And questions can make you want to learn more, right? There's just some really cool stuff. Well, we need to learn how to identify electrolytes. And so your book has provided this flow chart. So to identify an electrolyte, first ask yourself, is the compound ionic or molecular? And we should already know how to identify that, because in order to name them, we have to identify, is it ionic or molecular, so that we know which set of naming rules to use. So just to review, ionic compounds are going to either have a metal cation or the ammonium ion as the first part of their formula or their name. So ammonium chloride doesn't contain a metal, but it's an ionic compound because ammonium is a polyatomic ion. Calcium hydroxide is an ionic compound because it has a metal ion in it. So if it's got a metal ion in it, it's a strong electrolyte. So if it's molecular, then we have to ask ourselves more questions. Is it an acid? We've talked about acids. How can we recognize acids from their formulas? H starts with H. Okay? Acid formulas are generally written with the hydrogen ion first, the hydrogen being first. From the name, it's even easier. It says acid in the name, so that's always nice. So, is it an acid? If it's an acid, then you have to determine, is it a strong acid? There's only 7 of them. If it's a strong acid, it's a strong electrolyte. If it's not a strong acid, then it's a weak electrolyte. So there are a lot more weak acids than there are strong acids. Well, what if it's not an acid? It could be a base. So a base is a substance that produces hydroxide ions in solution. For our purposes here, the only one you really need to recognize is ammonia and some similar compounds. I would not expect you to know the similar compounds for an exam, but there are other weak bases. Ammonia is one that you should know, but you can also have things like CH3, NH2. In this compound, one of the hydrogens here has been replaced with this CH3 group. And that's getting into organic chemistry, but this is a relative of ammonia, where it's just got one of the hydrogens taken off and swapped for something else. That also acts as a weak base. So if it's not an ionic compound and it's a base, it's going to be a weak base and it's going to be a weak electrolyte. There are also strong bases, but they are all ionic compounds. And so they get taken out of this decision-making process up here because they're ionic and they are strong electrolytes. If it's not an acid or a base, then it's a non-electrolyte. So something like sugar, C12H22O11. It doesn't start with H. It doesn't have a metal in it or ammonium ion. It's not related to NH3. It's not an ionic compound. It's not an acid. It's not a base. It's a non-electrolyte. Okay, so we're supposed to classify each of these compounds as a non-electrolyte, a weak electrolyte, or a strong electrolyte. So let's look at this first one. This is methanol. And here's the formula, CH3OH. Is this an ionic compound? No. Is it an acid? No. Does it look even remotely like NH3? No. So what are we gonna say this is? This is a non-electrolyte. It is not going to form any ions when we put it in water. Methanol is very soluble in water, but it just separates into individual molecules and mixes. Okay, this one, sodium hydroxide, NaOH. Is it ionic? Yeah, it's got sodium in it. If it's ionic, it's a strong electrolyte. Yes?
Sodium hydroxide being considered a base?
Yes, sodium hydroxide is a base. It's a strong base. All of the strong bases are ionic compounds. Okay, this one. Ethylamine. Is it ionic? No, it doesn't start with NH4. Doesn't have a metal in it. Is it an acid? No, it doesn't start with H, doesn't have acid in the name. Does it look like it might be related to NH3?
Yeah.
Yeah, it does. Here's the NH2, and then there's something else on here. This is a weak base. Weak bases are weak electrolytes. So there will probably be some things like that that could pop up in the homework. But when you've got the homework, you've got access to the internet and to your textbook and all kinds of other things, and so you can manage through that. I would not ask you this one on an exam or a quiz or anything. I might ask you ammonia, NH3, and you need to know that that one's a weak base. Okay, how about this? Hydrofluoric acid. Is it ionic? No, there's no metal, there's no NH4. Is it an acid? Yeah, it's got the name acid in it. Then we have to ask ourselves, is it a strong acid? Well, there was 7 of them. Is it on the list? No. These are similar to hydrofluoric acid. Chloric, bromic, iodic, those are the other halogens as an acid, but hydrofluoric's not on there. Since it's not on the list, it must be a weak acid, and weak acids are weak electrolytes. In aqueous hydrofluoric acid, there are mostly HF molecules floating around mixed in the water. There's a few hydrogen ions, a few fluoride ions. It only ionizes a little bit. Any questions?